All right. Hi, everyone. Thank you for joining us today in a new episode of Doctor of Data Science. Today we have Zaim Awang. He's the co-founder and creator of iisara, and he's specialized in using the machine learning and artificial intelligence and making that possible in oil and gas. And then today he's gonna walk us through some of the use cases, and he will also discuss with us the subject of accessibility to artificial intelligence and machine learning tools in oil and gas. Zain, thank you for joining us today, and then looking forward to talk about all these subjects in oil and gas. Thank you.
Yep, thank you. Thanks for inviting me. It's my pleasure to be here. Looking forward to this.
Sure. First of all, I would like to hear about the iisara tool from you, and also would like you to tell us about or like talk to people who are new in the field of machine learning and AI in oil and gas, how to make the entry to that field, and then what are like your advices, or anything you can tell us. Yeah.
Fantastic. I think I'll actually start with how I got into this area. Is that okay?
Yeah, awesome. Yeah,
fantastic. So actually, I never intended to go into machine learning. So I started my career in oil and gas about more than 20 years ago. I studied petroleum engineering in Texas. So, and then I joined an oil company. So, from the beginning, I've always been oil and gas engineer, basically. So, I think it was right around, I think by now it has been like maybe 5 or 6 years ago. I'm a reservoir engineer. Basically, we solve, a big part of our job is optimization, forecasting. Basically, specifically, my job is to, design ways to basically get the oil out from the ground. Yeah. I mean, from underground. Now, the tricky part about trying to get oil from the underground is actually designing the blueprint on how to get it out. And why it's tricky is because you don't really see what's underneath there, right? Exactly. So it's a bit of a nightmare if you compare to other applications of data or engineering, in a sense that we know very little of what we're dealing with. So the only information we get, in a way, is like a seismic. It's basically seismic in some ways, but usually the resolution is very poor. So for those who don't know what seismic is in a way it's like MRI or X-ray, but we're doing it to what's there underground.
Yeah.
And then we basically poke holes. Basically, we drill wells. But that well is just 0.0001% of the area, the whole coverage area. So it's like trying to understand an elephant by looking at a 1 millimeter square area. It's very, very difficult to understand what's going on there. So we got pieces of data from our wells and some coarse information from the seismic, if we are lucky to have them. So with that, we have to basically deal with uncertainty, right?
Yeah.
And basically come up with a plan on how to, commercialize this energy underground. So that's the main challenge. So I have this bits and pieces of information. So I put that into my numerical model. It's not machine learning or AI. It's a simulator. So basically, I put those information in, and I was wondering how I can. So I get some results out. But the thing is, you basically have sometimes 10, 20 variables, and then you get one output variable. Okay. Now you want to see, okay, if I change one variable here or one parameter here, what would happen to the output? Okay, I can do that. I can just try, do some trial and error, put it through the simulation. But the simulation usually takes like maybe easily a couple of hours.
Exactly. Yeah, I've seen this before. I've been in the same situation. Yeah.
Okay. Fantastic. Yeah. That's the problem that we have. So it's very, very expensive, if not in terms of gathering data. It's actually in terms of the time it takes to just get one point of results. Okay.
Yeah.
And now we have, let's say, 20 different variables. I would really, really take a huge number of simulation runs, which can take days or weeks or even months to get some useful results. Okay. Right. Maybe I want to step back a bit, and basically for those who are not familiar with the problem we're trying to solve. So it's a bit like if I take an analogy of we're trying to understand what the blind man and the elephant, right? So that's what we're trying to do. We don't really know how the elephant looks like.
Exactly.
And then it's not even 5 or 6 people, blind people trying to understand what this is and communicate with each other. It's actually we're covering an area of a small area of the elephant. It's not even us grappling and touching the elephant.
Exactly. And you're trying to generalize this to the whole view.
Absolutely. So indeed, trying to generalize it and trying to come up with the bigger picture. So that's the challenge. So I said, okay, there must be. So I thought to myself, there must be an optimization or regression tool. Bear in mind, at this point in time, I don't even know what machine learning was. Okay, so I said to myself, there must be some sort of regression tool I can use to see the bigger picture, to visualize the picture. So what I did was to basically, typically I just put it into Excel. That's what I did. But it's always, us humans can only see 2 dimensions or 3 dimensions. And trying to regress. So I found softwares that can maybe allow me to have 2 or 3 dimensional regression, but there's not enough. There's no equations that can describe or curve fitting algorithm that can easily describe the nonlinear problem that I had, right?
Exactly.
Yeah. So it's definitely nonlinear, and it's definitely unpredictable. You can't just fit an equation, and furthermore, you have more than 3 variables. So there's a challenge of not understanding the big picture, not having the equation, and worse, I don't know if it's worse, but probably one of the worst things is that you don't have enough data.
Yeah, that's
right?
true. That's the main thing. Yeah, exactly.
Yeah. So I thought about it. There must be a way. So I struggled a little bit. I couldn't find the software. Excel was no good. So I said, okay. So I thought to myself, and I was being naive. I said, there must be a way to develop, a way to visualize this. So I set about doing that, and of course, there was nothing easily available to dimensionalize a 10 variable problem. I should have known from the start, but I kept on going and said there must be a way. So it actually turned into a side project that I was so enthusiastic with, and I think I was naive enough, at the same time lucky enough to not understand that no automatic regression for 10 variables exists yet. Okay, so I set off. This may be a little bit shocking to many, but I actually set off creating an algorithm for that. It was a journey that took me about a year to fine tune that problem. I was running a consultancy, so I have a young, fresh graduate petroleum engineer. Initially, he was trying to code it for me. So initially, being a fresh grad petroleum engineer, he was actually doing it with spreadsheet,
Yeah.
And then at some point, I encouraged him to move to Visual Basics. Then we realized that Visual Basics for applications with Excel, Excel just keep on crashing and it's just too tough for Excel. So then we moved on to Python eventually. Initially, he was very hesitant about it, but because he didn't even know Python and he was not into coding.
Exactly, yeah.
So he took it up and he helped me code the algorithm. So basically that it's like more than a year almost a year to basically develop the algorithm itself. I'm not talking about then coding it. So just developing the
develop the
algorithm,
algorithm, yeah.
lots of drawing on whiteboards, it's nothing like the social network movie where Zuckerberg drew it on the window, nothing like that, but lots of drawing on the whiteboard, like
So
a math professor sometimes.
So to this point, you were trying to model the production, the expected production, right? What was your target variable, or like what was your target in all this algorithm? What you were trying to predict?
Okay, I forgot to mention it. So in that specific problem, in that specific use case, it was more of what do I have a blueprint, because I was building a model.
Yeah.
Do I have a model that can describe the data that I'm seeing? So basically, I have pieces of data, production data, pressure data. So it's like you're a doctor, and then you basically have some
lab tests,
minor data from the patients, maybe some very few blood tests, and some other diagnostic tools that you have used. So very few pieces of data. So you're trying to describe the patient as a whole.
Okay.
From the pieces, the very big pieces. So I'm trying to describe the structure of the reservoir from the small pieces of data. Now, if I describe it correctly, I would have a small error in my model, because we're trying to match actual data and then for every realization, for every model that we have, you can basically simulate the output.
Yeah.
Right. So basically, let's say we poke a hole, and we basically have a pressure reading, right? So if we have described the reservoir correctly, the pressure reading over time would match the actual data that we have.
So to this point, you were trying to create your. I mean, I'm trying to relate that to the like, for example, the CMG simulation and reservoir.
Yeah.
So you were trying to set up the reservoir model and maybe to get to the step of the history matching with like a very reduced.
Right. Yeah. I didn't use a history matching because I mean some people are not familiar with it. Yeah. So definitely we're trying to history match the data. Now, I mean, just for the general viewers, the usefulness of that is that once you have a good description of by going through several iterations, normally many iterations, once you have a good description of your reservoir, you can then plan for the development of the reservoir, right? You can then say, okay, I can put X number of wells at these certain times and produce Y number of barrels of oil or gas, certain time, and I can get this much, so that I don't lose my shirt, by putting into many wells or whatnot. Right? So basically, that's what we're trying to do. We're trying to get a good description of the reservoir so that we can come up with a forecast, depending on what we plan to do, depending on how we want to develop, and therefore we can also come up with an economic forecast, or we can assess the commerciality of the project as a whole. Okay, because the reservoir can be too small, right? Or it can be too big that we're not really. It can be too small that we're not commercializing it. We're not able to make profit out of it, or it can be too big that we are not utilizing our resources, or we are not basically developing it to the our advantage, right? So so it's basically trying to come up with a good description. So this is a bit of a complex problem because of the reasons I mentioned. You don't really see the data. You don't have little data. Simulation takes a long time, and so on. But there are other similar problems in oil and gas which are much simpler. Like you're trying to predict from certain amount of data what you can see from, let's say 50 meters away. Let's say you drill a well. I've seen this 200 meters away. I've seen this. What can I expect? Maybe 50 meters away, something in between, and so on. So that is another way to describe the reservoir if you have enough wells. And that's in a way that's a simpler problem. because you probably have more data, right? And you're not trying to basically describe the physics, because when you talk about production or pressure, you're talking about it's not just how the reservoir looks like at that point in time, but as you produce or as you extract the oil, how it will change over time as well.
Exactly.
So this is like a more than a 4-dimensional problem, because you also have the time element as well.
You have like
right?
a couple of systems are working together, and they're like interacting with all the others, especially like
Absolutely.
when you have
You have the distribution of the rocks.
Yeah.
You have the fluids itself moving through the pores, and then you have what we doing to the reservoir,
model, yeah,
putting in wells, right? Now the other tricky part is that it has to observe the law of physics. So it's not just we go in and see what's there, because of the the change over time. It has to observe the mass balance, so we cannot take out more than what we have. For example, the energy has to be conserved, and so on. So there's many different equations that have to be satisfied in order for us to solve that problem. Now, of course, when we're using machine learning, we basically try to imitate that without using the equations, right? But still, it's a very complex problem to start with. Now, so that was what I was attempting. Back to your question. Sorry, a long answer.
No.
It's a specific use case, but then I thought to myself, I'm not just going to develop whatever I'm going to develop now will be applicable to a similar problem, because it's much harder to develop something very specific, sometimes, than to develop something more general. Because if I try to develop something more specific, as soon as I step out from that problem, whatever I've developed breaks down. I can't reuse it anyway. It's a very inefficient way for me to work. So bear in mind, I'm a reservoir engineer. I was a reservoir engineer. I still am. At that point in time, I'm trying to think. I was trying to be a bit smart to say, okay, let me develop this tool that I can reuse again and again and again. So maybe the reservoir changes, maybe even the problem changes. But at the end of the day, I'm just thinking like an engineer. It's an optimization problem. So I can apply it to economic forecast. If it's an optimization tool, I can apply it to any kind of oil and gas problems, even finance, stock market, and so on. So I was thinking in that manner. Let me develop something, and I'm sure it can be done. I was really naive. So I that's what I did. So within about a year, I borrowed concepts from definitely from petroleum engineering, from geoscience, but I also developed concepts from borrowed concepts from other areas. I think for the financial market, I borrowed a concept from geoscience. I developed a concept, and then I kind of like merge the concepts. I'm not talking about specific use case. I'm talking about what is the concept that I can apply. From first principle, I take it from the financial market, which is like how do we handle noise from the financial market, right? So just the general concept of it, and then from the geoscience perspective, from the oil and gas, I took the concept of day in and day out we map uncertainty. So how can I, in 3 dimensions, so how can I borrow that concept and map uncertainty in 4 dimensions, 6 dimensions, 7 dimensions, 8 dimensions? So that those concepts I brought together into an algorithm that can be used for optimization. So this is the cool part about this. Because I borrowed concepts from different domains, it became a general all-purpose optimization tool. Okay, right. And I actually filed for a patent, and it's patent pending.
Great.
So
let me ask you this question, Zaim, since you brought the subject of the uncertainty. So was there any consideration to implement any methods to perform data validations before you use the data, or did you look into the subject of the data validation, or how to perform your data quality The reason why I'm asking because I see this issue a lot in oil and gas data, especially, and then I don't see there is a lot of attention to let's say the step of data validation before the data usage. I would like to hear like your opinion about this.
Okay, so the reason why you don't see a lot of the data validation, and then I'll come to, you know, I'll address that from my perspective, but just to answer in general first, the reason why you don't see many of the data validation in oil and gas is sometimes because data is expensive, and sometimes we don't even have enough data. Yeah. Actually, lots of time we don't even have enough data. So, I mean, it's quite challenging to apply machine learning, traditional or conventional machine learning, to oil and gas problems, you know, to especially upstream. Okay. Yeah. When you talk about downstream, you actually have meters that, you know, gather data every seconds and so on. So that's a different problem altogether, and they do validation there. But if you talk about upstream, where just to drill a well may cost you $5-10 million. Yeah. Right? Yeah. So data is very, very, very expensive. So we're not talking about data that you can collect by having a sensor. No, you actually have to go underground, right? To get those data, and they're not cheap. So basically, that's one reason why we haven't seen lots of application in oil and gas, because data is so expensive. So that's just the general condition of it. So if you want to apply, let alone trying to do validation, trying to apply itself is a challenge. And now we're getting a little bit into the topic of, you know, getting into AI, right? In the oil and gas, right? So basically, that's a very big challenge. Now, why there's not much of validation? But to start with, there's not much application. So you may sometimes see certain professors or some individuals, you know, giving talk on AI in oil and gas, and they usually talk about hybrid models, where you basically have the physics and the machine learning combined, right? And sometimes it's called maybe top-down approach or something like that. But in some ways, it's still using, it still have to anchor to some physics or to the model per se, right? Because it needs to, you need to generate synthetic data sometimes to compensate for the lack of data.
For the lack of data. Yeah, exactly. Yeah.
Right. So that's why you don't see validation. Now, from where I was coming from, and this is like a journey that I went through. Like I said, I wasn't familiar with machine learning, right? But at the time, you know, machine learning was getting starting to become popular to the mass. Yeah? But still, at that point in time, people are not very familiar in general with the term machine learning. And this is like 5-6 years ago. I'm talking about general population. Yeah. Right. Artificial intelligence. So basically, so it was still kind of unfamiliar territory, and especially to me at that point in time. But I started to hear about it. But at that point in time, I already developed the algorithm, independent of machine learning. So I've developed this completely, I didn't even know it was new algorithm, but I developed this completely new algorithm without knowing what machine learning and AI, which was a good thing, I think, because if I knew what machine learning and AI was, I probably have gone down that path. Yeah. Right. And I wouldn't have developed a completely new technology. I would just use whatever was available. But I was not aware of that. But after a while, I started to hear about it, and I don't know. Have you heard about this Saturdays AI or AI Saturdays? It was kind of popular like a few years ago, and they do this Saturday meet up, AI Saturdays, in different cities around the world. Okay. So it's basically for people to get to know AI, what AI is. A lot of newbies, but there were some facilitators who are somewhat familiar with machine learning. So I actually went there. I actually, you know, from the start to, and there was like maybe 200 to 300 people who started on the first session, Saturday session. Bear in mind, it's a whole Saturday. So you basically lost 50% of your weekends every Saturday, every week, right? So it was like initially 200 and 300 people in the big auditorium or whatever. I think the organizer was borrowing Mind Valley auditorium at that point in time. So there were 200 to 300, and then it whittled down to, at the end, maybe to 20 or less than 20, right? But yeah, so I went through the whole of that just to see if I actually created something new, but also to learn, what machine learning and AI is. So at the end of this, semester or whatever it's called, I think it was like 3 or 4 months of it. I came to the conclusion that I created something completely new, right? And it was, a lot of people was not convinced that I created something new. But bear in mind that when I created it, I did not know anything about machine learning and AI. So I was not influenced by deep learning or gradient boost or whatever algorithm there is, right? My objective was to be able to see the whole solution space. So if I have like 4 or 5 data points, I wanted to see how the solution space looks like. And the solution space later on I learned is that in deep learning, for example, it's actually not the solution space. It's more like trying to find the minimum error or local minima in gradient descent. So you can't really even see the whole solution space, but you kind of like, trying to find your way like a blind man through the valley to find the local minima. So it's far from having the whole solution space. So even until today, in machine learning, you don't have the capability, or it's not really feasible to basically. That's why they call it a black box, to basically see the whole solution space. So that's why you have XAI, explainable AI, right? You basically run a few scenarios trying to get a description of your solution space, but you don't. The primary product is not the whole solution space. But when I was trying to create this, I wanted to see the regression, the optimization, everything. So that was what we achieved with the iisara technology. So iisara stands for AI. AI is artificial intelligence, of course. Solution approximation with robust algorithm.
Okay.
So that's what iisara stands for. And so that's what we accomplished. So now going back to what you said about validation. So my first validation was an actual case, so study. So at that time, I haven't really participated in the machine learning or the AI classes, the AI Saturdays. So I didn't know the term validation or whatnot. But I knew I had to test this, right?
Yeah.
So I basically, I was working on a project, real project, and the same project I was talking about just now, the specific use case. And I wasn't getting the history match. I wasn't getting a description there. So my question now is, do I try more? And this is typically what's happening. Do I run another 200 cases, which will take me weeks to exhaust all possibilities to tell me whether I got the model completely wrong, or is there really, or I just haven't found a solution? So I don't really know. Is there a solution? I just need to work harder to find it, or there's no solution. You need to go back to your geologist, start from scratch from a model that looks completely different. So those are my 2 options. But now the machine learning is basically about trying to solve this kind of problem. I mean the algorithm that I developed. So I went through, at this point in time, my young engineer who was helping me have coded it in Visual Basics, not Python, in Visual Basic application. So he took this, put this into the Excel, the VBA, run through it, and it shows me that the best solution, it basically gives me the local minima, which is the error. Yeah. And even that error was so big that I just came to the conclusion that I do not have the right framework or the right starting point. So I need to go back. So it's not that I have to work much harder. I basically have to go back and go to my geologist who was creating the model, come up with somewhat different description of it. Okay. So that's what I did. So basically it worked. It worked. Basically, the geologist came up with a different model, and after that I tested it and it worked. So instead of spending weeks trying to work with model that was not really feasible or was not really the right model to start with, I cut my time by using the iisara algorithm to find the solution. So I was convinced already at that point in time that it looks feasible, this algorithm, and that was my first validation. Okay, so later on, of course, we thought about, okay, after going through the machine learning classes and whatnot, that we take part of the data and then the rest for training, and then the rest of the data we blind test, right? But at that point in time, I had very limited data, right? So I tested it on the whole data set, right? Yeah, so that was my journey on validation. But right nowadays, it's just common to basically take move aside some of the data, put aside some of the data for the blind test or for the validation. Now, back to what I said previously in general, that we don't have enough data, right? Typically. So when I was in oil and gas, because it's very expensive, right? Yeah. And machine learning in general, you require lots of data, and that's why the barrier to entry is high, right? To machine, and you don't really see machine learning being used a lot for history matching, for example, because it's kind of like chicken and egg. In order to use machine learning, you need lots of data. But by the time you have lots of data, or you have like 200 simulation runs, you don't need machine learning anymore.
Exactly.
Right? So that's why you don't see that a lot. So maybe there's one commercial software or two commercial software that has the machine learning, but it still doesn't work too well, because you still need to run like 200 simulation cases before you're able to use machine learning. So instead of maybe running 600 or 700 simulation runs, you can possibly live with 200s, but it's still 200s as opposed to maybe just 20. So my idea when I was creating this is that I didn't know this, it was impossible to work with machine learning with small data set. So that was what I designed the algorithm to work with, right? So it was designed with pattern recognition. So instead of, how machine learning works or deep learning works, that it's really linear algebra in a way, right? You have this input, you have this output, and you try to find, what numbers to
optimize what's in between.
Yeah, it's a fudge factor. So basically, that's why you need lots of data sets so that you can fill in all those parameters, right? You can find a curve fitting for the boxes of those variables. That's what it is, really, in simple terms. So I was not having that kind of mindset, because I wanted to have the algorithm works with minimal data set, right? So so my approach was, how does the human brain works? Because human brain can connect the dots, right? Easily. Like if you have a sinusoidal pattern in the beginning and at the end, we can connect the dots in between, right? But if you give it to machine learning, you don't specify any, you don't tell it's a time series or whatever. You just give it to a plain vanilla neural network. It can't do it, right? It will just connect the dots with maybe some sort of line, so it completely missed the pattern, right? So, but when it comes to Mother Nature, when it comes to oil and gas, there can be so many different kind of patterns. So it's impossible to use a time series algorithm and have it work. It's impossible to use recurrent neural network or neural network and have it consistently work. So I was looking for something that can first work with minimal amount of data. Secondly, I can see the whole solution space.
Yeah.
Right. So what I talk about just now about the financial market, trying to define what is noise and what is noise, and very particularly important is how we do it in oil and gas. How do we map uncertainty? So we can basically, in oil and gas, with very few data points, we can basically map the whole topography. It may not be accurate. The more data you have, the more accurate the map will be, but we can still map a 3D solution with very few data. So I was thinking, okay, I can practically combine these different domains and work. And if I know how the human brain also works, I can combine this with, you know, what I talked about just now, the geoscience, financial market, combine all those into and make it into an algorithm network. Because the human brain has this pattern recognition. I have a little bit of foundation I learned from the geoscience, right? How to map uncertainty. But I also can reverse engineer, or I thought I could reverse engineer how the human brain works, like how we could find the pattern. So I said to myself, okay, if I can find the pattern, if I can describe how my brain finds the pattern, I can convert that to an algorithm, right? And solve that issue. So that's what I did. So I said to myself, how can the mind decipher the pattern? You know, so that was the struggle over a year. I have some ideas about it, and after I think over a period of 1 year, we actually solved. It was not an easy problem. You know, that's one reason why it was never invented, right? It was never used. It was never created. So there were actually a series of maybe 3 or 4 problems that we had to solve for the algorithm to work. So it's not just the for the financial market, it's not just the geoscience idea, it's not just from the, a big part of it is of course reverse engineering how the mind works, right? There's a big part of it, but it's not the only part. So kind of like solve all these three to four these kind of problems, we came up with this algorithm. So that was that took me about a year, right? So I was trying to say how we did the validation. So after that, so in our case, it was not so much of a challenge anymore, because we have designed the algorithm to work with minimal amount of data, right? Because it works like a human brain connecting the dots.
Yeah.
Right. Now, again, a human brain can connect the dots easily in 2 dimensions. And then a lot of people, even engineers, have problems connecting the dots in 3 dimensions, right? But if we figure out how to put this into algorithm, then we can easily extend this to 3 dimensions, 4 dimensions, 6 dimensions, 7 dimensions. And that's what we have, real problems. We actually have 7, 8, 10 dimensions. Mother Nature gives us several different variables. For those who know the oil and gas or subsurface or upstream lingo, we basically have permeability. We have the rock properties like permeability, porosity. We have the fluid properties like viscosity. We have the structure, the faults, number of compartments, how transmissible are the faults, where are the fluids contacts are, the pressure, and so on. So many different kind of variables. And it can even be, it's not just one variable, because it can be heterogeneous and it can even change with time, right? So quite a lot of variables. So now, because of the way the algorithm is designed, it can work with minimal of data. So even if I have 20 data points, we compare this with normal, with conventional machine learning, we would need like 200 data points at least. Now with this algorithm, we need maybe about 20 data points to come up with a stable solution. So even with minimal amount of data points, we can take some of it away for blind testing, right? But if you try to use machine learning, even those 20 data points are not even enough for training, let alone.
Exactly. Yeah, that's like, very small data points.
Definitely a pain point. Definitely a pain point. So that's where we differ, and I was definitely lucky in the sense that I was fortunate that I didn't know that it was quote unquote impossible, or I'm really not going to the traditional method of machine learning or AI, or I was not challenging the best minds on working on machine learning AI. I was fortunate in that sense. I was naive that okay, it should be possible. Sure enough, it took us a year to do it. Yeah, definitely. So that's where we are right now. So I think like I think Jeffrey Hinton also said something similar in the sense that we need what we have right now is we need to come up with completely new algorithm. Jeffrey Hinton said this himself, right? He's the father of
he's the guru of the, I guess, new networks.
Exactly.
Yeah.
So even he himself said that we need to come up with something new, right? So in that sense, I feel that I'm in the right camp, doing something correct, right? So basically, I guess the message to sure enough we created our own algorithm, but I think for those who are inclined to work on algorithms, I know several institutions or several people are actually working on this one, but I think there's room to come up with completely new algorithms. And it's not just in machine learning per se. I would be more than happy to have other people come up with something completely different as well. Maybe at the end of the day we can combine this and come up with something even better, right? Rather than rehashing the existing one and fine-tuning the existing one. There's nothing wrong with that. The thing is it's a bit crowded and lots of people actually doing it already, but
Exactly,
we lack the effort to basically come up with something innovative because we thought that it's impossible to do it. If I knew machine learning at that point in time, I might have thought as well myself that how could I create something completely new? But I'm out here telling people that it's actually possible. I remember I just heard what Elon Musk said something that about technology. Technology even degrades with time. So we used to send people to the moon, and later on we use space shuttle to send people to the lower orbit. And after the space shuttle is retired, we don't even send people out to the low orbit or to the moon. So people, the Egyptian civilization, they knew how to create these pyramids, but they forgot about how to do it. And maybe the Romans or the Greeks, they figured out how to do these aqueducts, and they forgot how to do it, right? So actually, technology is very, very difficult if you don't put a conscious effort to create it, right? Sure enough, we have technological advancement, but imagine the whole global population. We have technological advancement coming from different corners of the earth because there are people intentionally working hard on it, and a lot of these are not through accident. It's not like a tree fall, apple fall in your head and you discovered the gravity. No, it doesn't happen that way. A lot of it is actually from conscious effort trying to come up with new technology or especially solve an existing problem. So that was where I was coming from. I was naive enough to think that I could do something, but at the same time I was trying to solve a problem that I had. So you don't really want to solve a problem that nobody has. So I think the key message I want to send out is that let us try to come up with discover new frontiers, be it in machine learning or any area that you involve with. And I think that's what makes things quite a bit more interesting, and that's where you basically become a net positive, become a force of net positive force by putting out something new, right? But from there are challenges. Like if I talk about a new technology like tonight, I think a lot of people will still be skeptical. But that's how it is. Adoption of technology takes quite a long.
Yeah, I think exactly.
A long path, right? I know it's a difficult path myself because I've been through it. So if you work on through this, you need funding, you need people to work with people. You need a strong team to continuously work against the conventional stream, for example. People who share your belief that you can make this work and things like that. Not just technically, but commercially. And commercial making it commercially viable is very important, because otherwise you can't sustain it, right? You do need, especially in the early days, you do need the funds to basically develop the technology and get it out and so on. So something that is, doesn't have commercial value, is very, very hard to sustain it. Right? So I mean, you can probably put it into the public, out to the public, but it's still going to take a long time for it to grow. So I think the hybrid approach, where you put it out into the public, but you get some commercial support, will tend to accelerate the growth of any technology. So I was talking about, okay, go out there, create, use your talent, if you have whatever talent that you may have, to push the frontier of the knowledge, create new technology, but then have a team behind you, or work with people, work with other companies, for example, to basically commercialize your product and put it out there, right? So that's what we're trying to do, and we basically working with a major oil and gas service provider to basically have this technology out, right? Okay. So I think, yeah.
I'm sorry. So is your tool available to, like, is it something available on the cloud, or like your let's say end users need to implement something on premises?
Yeah. The idea is that okay. So basically, when we first created it, we kind of like knock from door to door in a way, not literally, but in a way. We approach a potential client and say, okay, would you like to try this and so on? But we realized that this is not an efficient use of our time. We're coming out with something new. We don't have the backing of a brand name or big name. That it's trying to get this out to the public and trying to get this acknowledged is kind of difficult. Trying to commercialize it is very challenging, right? So we're trying to say that, okay, you have been using this technology and so on. So there's two camps. One is people who have been using conventional machine learning, right? Data scientists and whatnot, and we're trying to tell them that we have something new that you were not taught of in university or in your career. So it's like there's a mind barrier there for this new technology, for them to adopt this new technology. Now, that's from the data scientists. But if you talk about the general population, it is in a way that sometimes it can be easier, because they come with an open mind. They don't have a preconceived notion of what an optimization algorithm should look like, right? So they can be more open, but at the same time, you need to basically do a lot of hand holding.
Yeah.
Right? Because they're not used to this technology and what it can do for you. So in a way, for both cases, it is inefficient, because one camp may actually have somewhat of a preconceived idea and maybe reluctant to try something completely new. And then there's other camp with general population, where we have to do quite a lot of hand holding. So anyway, regardless, it's a long journey. And I realized that a few years in the journey, that it's going to be a long one. So so that's why we decided to basically work with a large oil and gas service provider. Then they have the willpower, they have the stamina, they have the clout to basically push this through. Now, I'm trying to answer your question whether it will be in the cloud or whatnot. So yes, it will be available in the cloud, because the ecosystem of this oil and gas service provider is in the cloud. So it will be available. So like I said, it's hard work trying to knock door to door and answer, one by one, a potential customer. Rather, we are actually waiting to get into the ecosystem, and then we let the oil and gas service provider release it to the oil and gas community, right? So that's where we are. I think I'm not sure if we can, come up with the mention the name of the our service company at this point in time. We have signed an agreement, but it's not really, but they haven't really, mentioned it yet to the public. So we
Okay.
don't want to jump the gun. But I think in the next maybe a year or so, God willing, we will have it out in the, at least in the oil and gas, for the oil and gas community, to test and work with it.
Awesome. Great. So we have 10 minutes left. I'm not sure if you have something or like a demo you can just like quickly walk us through the tool. If that's available, that would be great. Yeah.
Sure thing. Thanks. I think maybe if I may just show a video clip that will just take 54 seconds.
Yeah, I think it gives us an idea about your tool. Yeah.
All right, fantastic. Then maybe I just go through a demo that will just take 2 minutes. So I think that there'll be enough time. Okay.
Yeah.
So if you don't mind, I'll share my screen.
Sure. Yeah.
I'm not sure if I'm sharing the.
Yeah, I can see the web page.
Okay. So basically, anyone can go into our. So I won't spend too much time on this one, but you can basically play around with the demo. It's just www.iisara.ai/demo. So easy to recall. If you don't remember, so Sarah is very easy to remember. So you just remember AI in the beginning and .ai at the back, and then /demo, right? And Sarah is common name. Basically, it's also my daughter's name. So it's very easy to. Sarah is common name, so very easy to remember. I'm just going to show this video.
Okay.
So this is just an introduction to show you the flow of it. I think I need to play it first, then maybe enlarge. Okay.
Okay.
Without wasting much time, let me try to go to the demo. So I'm just going to run the demo on history matching. When you go to the demo page, you can choose a different kind of demo that you want. We have hyperparameter tuning, oil and gas demo. Some use cases includes log interpretation, log prediction, log values prediction, production forecasting, and history matching. So those are the 3 example use cases. And then there's also a general demo where you have simple data. You can basically plug and just upload the CSV data for you to play around with. But there's also a demo for medical use, for example, heart rate prediction, heart disease prediction, which is taken from the University of California, maybe data set. UCI, right?
UCLA,
yeah, UCI. So basically, and several other general data sets, fraud detection, and so on. Just to show the versatility of the tool. So this is hyperparameter tuning. Okay, so for the oil and gas, my bad, history matching. Okay, so basically, I can, so I'm just going to go into history matching. This is basically the problem that I described just now during the interview. I'm just going to use a sample data set, so I don't spend much time in the data set. We actually have the apology if this is alien to non-oil and gas. But basically, we have for data, permeability, multiplier, per volume. So basically, this is just parameters that describe the reservoir, the structure, right? And then this is what we aim for. So for every combination of it, it will yield certain error values. Now this you need some data to start with. So this data was produced from the simulations. But the thing is, we just require like maybe 20 different simulation runs instead of 200 to make it work. Now, you can then just gonna randomly choose 3 different parameters, because for the demo purpose, you can basically say why you wanted to choose, because you may say that, okay, this variable actually, I know for a fact that this variable has no impact on the outcome. So I'm not going to include it in the quote unquote training, right? So in this case, I just choose 3 variables to save time. And then you're asking like, what's the, what are you trying to achieve, right? In this case, we're trying to find the minimum error, because if we have the minimum error, what will give the minimum error? What combinations of this variable will give the minimum error? Yeah, because then there is likely, if I'm happy with that minimum error, there is likely what describes the reservoir, right? And I probably have a reasonably good description of the model of the reservoir, right? So the output here is filter matching error. And then I can also say, meanwhile, while it's trying to describe all the solution space, I can also put in, okay, if I have this variable input, what is the outcome? So it's like saying that if I do A, B, and C, what will be the outcome? If I drive 20 kilometers per hour through this road at this time, what time will I arrive at my destination? For example, right? So it's like, if I do this, this, and that, what will be the outcome? So typically, okay, and then I can then choose to view. This is what I mentioned by showing the whole solution space, right? So I hope we can see this before the end of the session. I know sometimes the network is a bit slow.
That's because it's a shared.
But I think we get it in a few seconds. If not, then it was basically what you seen in the demo. Okay, I think it's almost there.
It's loading.
It's just loading the 3D. Yeah. Okay.
Nice.
So here you can basically see the whole solution space, and this is the local minima.
Prediction.
Yeah, the prediction and the local minima.
So even the prediction is actually was achieved in a very great let's say minima. I mean, it's almost like the best solution available, I guess.
Yeah, definitely. And then you can you basically, the problem is that the human being can only see 3 dimensions. So I can choose to display other variables. So then I can basically see, if I do this, if I do that, what's the outcome, right? So a manager would want to say, if I drill this number of wells at this point in time, what is my output from cumulative? What will be my reserves? What will be my total oil produced in the future? So here the manager can say, okay, I don't want to see this. I want to see something else. So then I can plot something else and so on, right? So this is very, very, very important, because you don't have this. Remember, DARPA is spending like billions of dollars trying to solve explainable AI. In some ways, we have done this, to a large extent.
Yeah, exactly. And that's like the fact that the users, they can like interact with the model, they can like change stuff on the fly and then see the results. That's a very useful feature, and it's also kind of like removes some of the vagueness from the AI of like being a black box algorithm or something, and then people can definitely see what the model is doing, and then how it honors the physics.
Indeed. That's definitely very, 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 very important. Definitely. Yeah, I think that's kind of achieved what I wanted to do when I set my foot trying to do this.
Well, Zaim, thank you for your time today, and thank you for your patience of taking us through the journey of iisara, and then for the advices to people who are new to machine learning. I really appreciate that, and wish you best of luck. Also, thank you for managing this in the 2 different time zones. I know it's difficult to schedule things like in 2 different time zones. So I really appreciate that, and then I hope we will talk to you soon. Thank you so much.
Thank you so much. It's